Hello everyone, welcome back. Today in this video lecture we'll discuss the theories of bonding in coordination compounds, or how coordination or complex species forms bonds, that is the nature of metal ligand bond that is formed in complex species. So starting with the nature of bonding between the metal and the ligand in coordination compounds, we'll start with the first theory, that is Valency bond theory. Valence bond theory. Is VBT. So we'll discuss what is valence bond theory and what are the various postulates of valency bond theory, and in this we'll discuss different types of complex like octahedral complex, tetrahedral complex, square planar complex, and what are different types of hybridization that is used for formation of bond between metal and the ligand. So starting with this valency bond theory, this theory is due to Pauling and Slater. These are the two scientists who gave this theory, valency bond theory. Now valency bond theory, or simply VBT, takes into account the electronic structure of the central metal atom or ion in the ground state. So central atom or central metal ion, the electronic configuration or the electronic structure of these ion or atom in the ground state, takes into account the hybridization, the structure, magnetic properties of the complex. So takes into account the electronic structure of central metal atom or ion, hybridization, shape, geometry, and magnetic behavior of complexes. So after studying this valency bond theory, we should be able to predict what is the electronic configuration of the central metal atom or the ion in the complex, what is the hybridization of central metal atom or ion, what is the shape or geometry of the complex formed between metal and ligand, then what is the magnetic behavior, whether the complex will show paramagnetic or diamagnetic. That is what we call as magnetic behavior of the complex. So we should be able to answer these questions after studying this valency bond theory. As I told you earlier, this valency bond theory is based on certain postulates. So coming to the postulates, of this valency bond theory. An important first postulate of this valency bond theory is the metal atom loses electron and is converted into metal ion before the formation of complex. Though there are many complexes in which the central metal atom exists in zero oxidation state, but majority of the case, the central metal loses some electron and is converted into the metal ion, and the charges on the metal ion is equals to the valency of the metal ion in the complex. So the central metal loses electron and some electrons and forms cation, and that is what we call as the oxidation state of the metal ion. Oxidation state. Second, now in this theory, one of the most important criteria is the hybridization of the central metal atom or the central metal ion. Now, in the first postulate we say the central metal loses some electrons and is converted into cation. Now, after this metal forms metal ion by loss of electron. This metal ion makes available equal number of vacant s, p and d orbitals equals to the coordination number of the metal ion in the complex. The second postulate says central metal ion makes available vacant s, p and d orbitals equal to the coordination number that means if the coordination number of the metal ion in the complex is 2, so this will make available 2 orbitals. If the coordination number of the central metal in the complex is 4, then the central metal will make available 4 unoccupied vacant orbitals. If the coordination number is 6, the central metal will make available 6 unoccupied vacant orbitals. So this availability of the vacant orbital is also very important. Next, these vacant orbitals of the central metal undergoes hybridization to form equal number of hybrid orbitals, and these hybrid orbitals are equivalent in energy and they are directional in nature, means the hybrid orbitals are directed in space in such a way that the distance between the hybrid orbital is maximum or the energy between the hybrid orbitals is minimum. Vacant orbitals undergoes hybridization to form hybrid orbitals. The number of hybrid orbitals is equals to the number of atomic orbitals that has been mixed. The hybrid orbitals are equivalent in energy the hybrid orbitals are equivalent in energy and is directional in nature. That means they are directed in certain direction in space. As I told you, why this is directional, because we have to place electrons in these hybrid orbitals. When we place electrons in these hybrid orbitals, these electrons should have minimum repulsion to have this minimum repulsion, the distance between the hybrid orbitals should be maximum. So that particular state, when the repulsion between the electron pair is minimum, the energy will be minimum. As the energy is minimum, that particular orientation or the state will be the most stable, and this directional nature gives rise to the shape of the complex. So I repeat again, they are equivalent energy and directional in nature. Directional in nature, and this direction gives rise to the shape or the geometry of the complex. Orientation or the directional nature means the hybrid orbitals are directed in such a way that the distance between the orbital is maximum. As the distance is maximum, the repulsion between the electron pairs will be minimum. As the repulsion is minimum, energy will also be minimum, and that particular state will be the most stable form. So this directional nature is responsible for the stability, shape or geometry of the complex. Next, now once the hybrid orbitals are formed, these hybrid orbitals being vacant, these hybrid orbitals overlap with the filled sigma orbitals of the ligand to form a coordinate or dative bond. That means the metal orbitals being unoccupied, vacant, the pair of electrons should be coming from ligand only. Since both the electron is coming from ligand only, the bond formed between the ligand and the metal ion is predominantly coordinate or the covalent bond. So the ligand should have at least one lone pair electrons to donate. Then the vacant hybrid orbitals of central metal ion overlaps with the filled sigma orbitals of ligand, forming a coordinate or dative bond, which is represented as, look at this, we have this central metal atom or ion. This contains vacant hybrid orbital. To this vacant hybrid orbitals, electrons are donated from ligand. So this is ligand. Ligand is donating a pair of electrons from its filled sigma orbital to the vacant hybrid orbital of metal, forming a dative bond. So this bond formed between metal and ligand is a coordinate bond or dative bond. This is a dative bond that is formed. In addition to this, dative bond formed between metal and ligand by transferring a pair of electrons from filled sigma orbital of ligand to the vacant hybrid orbital of metal. In some of the case, a pi bond may also formed by transferring a pair of electrons from filled d orbital of the central atom to the vacant orbital of the ligand. Sometimes a pi bond may also form by transferring electrons from filled d orbital of metal to the vacant orbitals of ligand. That is, we have this metal, this ligand. So first look at this, ligand is transferring a pair of electrons from its filled sigma orbital to vacant hybrid orbital, forming a sigma bond. In the second case, this metal may transfer a pair of electrons from filled d orbital to the vacant orbital of ligand. So in this way, a double bond may also form between metal and ligand. So this is sigma bond, this is pi bond. So this is the case when the ligand has vacant orbitals which can accept electrons from the central metal. These type of bonds is normally formed when metal is in lower oxidation state or zero oxidation state, and the ligand contains unoccupied anti-bonding molecular orbitals. But basically what I am saying is, whenever a bond is formed between metal and ligand, electron is always transferring from ligand to metal, forming a dative bond. This is with only very specific ligands only, but this is the general form for all metal ligand bond. Then next postulate is, now while formation of hybrid orbitals in octahedral complex, the d orbitals are always used. Now the d orbital used in hybrid orbitals may be inner orbital n-1 d orbitals or the outer shell or the Valency shell nth d orbitals. So d orbitals involved in hybridization may be inner shell n-1 d orbital or Valency shell or outer shell and d orbitals. So two different types of d orbitals may be used depending on the nature of ligand that is used in complex. Then next postulate regarding this valency bond theory is, now under the influence of ligand, the electrons in the d orbital of the central atom may forcefully pair up against Hund's rule. Now Hund's rule says pairing of electron takes place only when all the same energy levels are first occupied, singly occupied. But in formation of complex, under the influence of ligand, some of these d orbitals may forcefully pair up against the violation of Hund's rule. That may be possible, but that all depends on the nature of ligand that is to be bonded with the central metal. Electrons in d orbital may be forcefully paired off under the influence of ligand, that is violation of Hund's rule. That means while writing electronic configuration in complex, sometimes the central metal atom in complex may violate this Hund's rule, and that is against the violation of Hund's rule, and that is possible only when we have ligand, that is strong field ligand, which can exert strong influence on the central metal atom, and this may forcefully pair up electrons. So electrons may pair up in d orbitals. Now, in presence of ligand, electrons are transferred to the central metal, or in presence of ligand, electrons may be forcefully paired up or may not pair up, depending on the nature of ligand or the availability of the d orbitals for hybridization. If the d orbital contains any unpaired electrons, then that complex will show paramagnetic behavior, or if there is no unpaired electrons present, then the complex will be diamagnetic. So magnetic behavior, this may be paramagnetic due to the presence of unpaired electrons, or this complex may be diamagnetic, that is complete pairing of electrons. So to decide this magnetic property, we have to see whether the electronic configuration of the metal ion in the complex contains any unpaired electrons or not. If the presence of unpaired electron is detected, then the complex will be attracted by an external magnetic field, and that is what we call as paramagnetic. And if the complex metal ion in the complex doesn't have any unpaired electrons, or all the electrons are completely paired up, then that particular complex will be repelled by an external magnetic field, and the substance repelled by an external magnetic field are known as diamagnetic. So from this we should be able to predict the magnetic behavior of the complex. So these are some of the postulates of valency bond theory. Based on these postulates, we will discuss the theories of bonding in octahedral complex, tetrahedral complex, and square planar complex. So first we will take up octahedral complex, means valency bond theory in octahedral complex. So we'll start with octahedral complex. Octahedral complex. Now the octahedral complex formed by the central metal ion or the central metal atom is of two types. First one is known as inner orbital complex. Now look at it, this is only for this octahedral complex. Inner orbital octahedral complex and outer orbital octahedral complex. So in this we'll just discuss the best definition or the difference between these two. Now an octahedral complex is known as inner orbital complex if it uses n-1 d orbitals for hybridization, where n is the valency cell. So if the d orbital used is not from the valency cell or is from n-1, where n is the valency cell, then these types of octahedral complex are known as inner orbital octahedral complex. Whereas in case of outer orbital octahedral complex uses nth d orbitals, that is d orbitals of the valency cell. So if the d orbitals used in the hybridization is from the valency cell, that is nth shell, where n is the valency shell, then this is known as outer orbital complex. Whereas if the orbital used for hybridization is from the inner shell, not from the valency shell, that is n-1 d orbital, then this is known as inner orbital complex. Now in inner orbital complex, the hybridization of the central metal is D2sp3. So total number of hybrid orbital is 6. 3, 4, 6. 6 hybrid orbitals of equal energy or equivalent energy. So look at this. In inner orbital complex, we use d square sp3. Outer orbital complex, that is sp3 d2. So look at this, the difference in writing the hybridization. If I say d2 sp3 means this is the n-1 d orbital, inner orbital. If I say sp3 d2 means this is the outer shell orbital or the valency shell n d orbital that is used. Now S has got one orbital, so there is no problem in the orbitals of S. P has got 3 orbitals, px, py and pz, all the 3 orbitals are used. Now the problem lies with D. Now D has got 5 orbitals, so out of these 5 orbitals, 2 d orbitals should be selectively used for this hybridization. So now the question arises, which d orbital should be used for hybridization? Now the d orbital used for this hybridization is dx square minus y square and the dz square. These two orbitals are the orbitals whose lobes are directed towards the axis. This is purely along z axis, this is purely along x axis and y axis. Now we have P whose direction is along x, y and z. So z will overlap, x will overlap, y will overlap. So this is how we select the orbitals for hybridization. So selectively you have to use this x square minus y square z square, but these two orbitals has orientation along axis. Similarly, in this outer orbital complex, the d orbital used is dx square minus y square and dz square. Again, because of the same reason, because this has orientation along x axis, y axis and z axis, we can have maximum overlap. Now look at this. This inner orbital complex uses lower energy n-1 d, because when we compare the energy of n-1 and d, obviously energy of n d orbital is greater than n-1 d. Now in this inner orbital complex, lower energy n-1 d orbital is being used. The energy content of this energy orbital is less than the energy content of the outer orbital complex. Since the energy content of this inner orbital is less, these inner orbital complex are more stable due to lower energy n-1 d orbitals. Since higher energy d orbital is used, so this is less stable. So outer orbital complex are less stable, whereas inner orbital complex are more stable. If inner orbital complex is more stable, then this is less reactive or less labile. So inner orbital complex is more stable, less reactive or less labile. Labile means in terms of reactivity activity. If the outer orbital complex is less stable, then there is a more reactive or more labile. Now inner orbital complex more stable, less labile when we use n-1 d orbital. So the inner orbital complex forms mainly covalent, whereas outer orbital complex, the metal ion is using the higher energy n-1, nth d orbital. So these forms ionic. Now these inner orbital complex, the lower energy n-1 d orbitals are used. So these complexes are known as low spin complex or spin pair complex. Low spin or spin pair complex. That means in these types of complex, under the influence of ligand, electrons in d orbital may be forcefully paired up. If the electrons are forcefully paired up in the d orbital, the resultant spin quantum will be less. So this is known as spin pair. If the pairing of spin occurs, then the total resultant spin quantum number will be less. So we say this is low spin complex. Now in case of outer orbital complex, we are using higher energy nth d orbital. As a higher energy nth d orbital is used, the pairing of electron is not possible in case of outer orbital. If the pairing of electron is not possible, then we say this gives you high spin or spin free complex. High spin or spin free complex. So this is the basic difference between, or the comparison between, inner orbital complex and outer orbital complex. So we'll explain this inner orbital complex formation and outer orbital complex formation. So I hope you understand what is the meaning of inner orbital and outer orbital. Basically is here. Inner orbital due to the use of inertial lower energy n-1 d orbital. Outer orbital complex due to the use of higher energy or Valency cell nth d orbitals. Now coming to this inner orbital and outer orbital complex, we'll explain by use of an example. Let's take this by taking this cobalt here. So we have this cobalt, atomic number 27, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3p7, 4s2. This is the electronic configuration of cobalt. So if you look at this, we have 7 electrons in d orbital, 3d, and 2 electrons in 4s. So after this 4s, 4p is unoccupied, 4d is unoccupied. So this is the valency cell, that is cell next to valency cell. Now let's consider this cobalt plus 3 ion. So we have to remove 3 electrons from neutral atom. So first these 2 electrons from s orbital should be removed, then the third electron should be removed from 3d. So I'm just writing the Valency shell electronic configuration. So we have 3d6 and 4s0, 4p0 and 4d0. So we remove 3 electrons, 2 from 4s orbital and 1 from 3d. So if you look at this, this is we have 3d, this is 3d, we have 6 electrons here. This is 3D. Then we have 4s, no electron. Then we have 4p, there is no electron. Then we have 4d, again no electron. So this is the central cobalt plus 3 state, that is the ground state. We have the ground state electronic configuration of cobalt. Now this cobalt plus 3 forms complex with 6 ligands, that is octahedral complex. Now this forms the COL6. This may have plus minus charge depending on the nature of this ligand. So now the question is, this may undergo inner orbital complex or may undergo outer orbital complex. So there are two possible cases that arise here. Now suppose if this forms inner orbital complex, suppose let's assume that this forms inner orbital complex. Now inner orbital complex n-1d, that means we have to use 3d orbital. But if you look at this electronic configuration of cobalt plus 3 in the ground state, there is no vacant d orbital. So first thing is, to form this hybridization, this central metal has to make some vacant d orbitals. So at least 2 d orbitals should be vacant. So under the influence of this ligand, electrons in 3D are forcefully paired up so that 2d orbitals should be available. So look at this, cobalt plus 3 in complex. Here we have, look at this. So initially we have 2 electrons here. Now we have 1 electron here. Now the second electron is forcefully paired up here. So this electron is forcefully pairing with this electron, and the third electron pair, this electron is again forcefully pair up this electron. So look at this, though we have 5 same energy level, so these under the influence of ligands, electrons are forcefully paired up in the 3d orbital so that 2 vacant d orbitals is available for hybridization. This is what we call as the violation of Un's rule that we have used in the postulates of Valency bond theory. So ligand which is forcefully pairing out the electrons of the metal ion is known as strong field ligand. So we have the strong field ligand. So under the influence of this ligand, electrons are forcefully paired up in the d orbital. So this is 3d orbital. So this d orbital is dx square y square, and this must be dz square. Then we have 4s, then we have 4p. So now we have 6 orbitals, 2d orbital, 1s orbital, and 3 p orbitals available. Now these 6 orbitals undergoes intermixing, that is what we call as hybridization. So when this mix, this forms hybridization, that is D2sp3. So look at this, d orbital is 3d, this s is 4s, p is 4. So we are using n-1 d orbital. Now this cobalt plus 3 now forms cobalt ligand. Now each ligand will be transferring a pair of electrons. So we have this ligand, Now this a ligand here, second ligand, third ligand, fourth ligand, fifth ligand, sixth ligand. Now we have 6 vacant orbitals, and each vacant orbital is having a pair of electron from ligand. Now this ligand is transferring a pair of electrons to this. So we have electron pair here. These electrons are coming from ligand, this is from central metal. Now look at this. After this formation of complex, under the influence of this ligand, electrons in d orbitals are forcefully paired up. Since electrons are forcefully paired up, if you look at this electronic structure of this cobalt plus 3 in the complex, there is no unpaired electrons. So since look at this, the resultant spin quantum number is 0, there is no unpaired electrons. Since there is no unpaired electrons, so spin is low. We say this is low spin. So all these spins are exactly cancelled out. So resultant spin quantum number S is 0. Since there is no unpaired electrons, all the electrons are completely paired up. So we say this is low spin or spin pair complex. Now since electrons are completely paired up, so we say this is more stable, less reactive. On the other hand, now look at this. We assume that this forms outer orbital complex. So the resultant spin magnetic moment, that is n plus 2 under root. So n is 0. So the resultant magnetic moment is also 0. Outer orbital complex. So ligand being weak cannot force the electrons to pair up. If ligand cannot force these electrons to pair up, so there is no vacant 3d orbital. Since there is no vacant 3 orbital, then the only option left is he has to use the valency cell for D orbitals. So therefore look at this. This cobalt in complex will have this is 3D. So we have 6 electrons, then we have 4s, then we have 4p, then we have 4d. So this is 4s, 4p and 4d. Now since ligand cannot force these electrons to pair up, no vacant d orbital is present in 3d shell or third shell, so it has to use 4th d orbital. So these undergoes intermixing to give 6 equivalent energy hybrid orbitals. Now since it uses valency cell d orbital, hybridization is sp3d2. So s is from 4th shell, p is from 4th shell, d orbital is also from the 4th or the valency cell. So these 6 hybrid orbitals now forms complex ligand. So we have this ligand, and each ligand will be transferring a pair of electrons to the vacant hybrid orbital, resulting in the formation of the complex. So we have 2 electrons here. This is how complex is formed. So if you look at this metal ion in this complex has got some unpaired electrons. Due to the presence of these unpaired electrons, we say this is high spin. The resultant spin quantum number is high. So we say this is, if you look at this, resultant spin quantum number is plus half plus half plus half, so this is 2 for unpaired electrons. Now since unpaired electron is more, we say this is high spin or spin free. So resultant magnetic spin quantum number is n plus 2 under root bm. So n is 4, 4 plus 2 6, 6 for 24. So we have high spin complex. Now since even after the formation of complex, these complexes having some unpaired electrons, due to the presence of these unpaired electrons, these complex can easily accept undergo oxidation or reduction. So this is what we call as more reactive. So the reactivity is due to the presence of this unpaired electrons in the 3D orbital even after the formation of the complex. So this is how octahedral complex inner orbital and outer orbital is formed. So for this to define, we should be able to know the nature of ligand, but valence bond theory says nothing about the nature of ligand. So we can simply say if the magnetic quantum number, spin only magnetic moment is low, then this must be inner orbital complex. If the spin only magnetic moment is large, then that complex may be outer orbital complex. So this is the difference between inner orbital and outer orbital complex. So let me just give you some electron configuration of different types of d orbitals for this octahedral complex. So this is inner orbital, this is outer orbital complex. So we have dx, suppose we have d4, because in case of d3 already we have 2. Okay, like this d3 inner orbital. So we have this is 3d. We have 3 electrons here. So already we have 2. So number of unpaired electrons, we have 3 unpaired electrons. D4 type, D4 type. If I place 4th electron here, so the only one d orbital is vacant, but inner orbital requires 2 3d. So this electron will be forcefully pair up here. If the electron is forcefully pair up here, the number of unpaired electron is 2 here. D5. Now in D4, look at this, we have 2. In D5, we have 1 more electron, so the second electron will be forcefully paired up here. So number of unpaired electron is 1. D6, the 6th electron will be forcefully paired up here. So we have this. So number of unpaired electron is 0. So inner orbital complex D6 type will have number of unpaired electrons 0. If suppose we have this D7 type, already the 6 electrons are completely paired up here. Now we have 7th electron. This is 3d. Then we have this 4s. Then we have 4p. Then we have 4d. So this electron is transferred from this to this orbital. So So how many unpaired electrons left? One unpaired electron. So these undergoes hybridization. The seventh electron will be transferred to the higher energy level. Similarly, we have D8. So we can have 6 electrons here. Then we have 4s, 4p. Then the 7th electron and the 8th electron will be transferred to the higher energy level. So the number of unpaired electron is 2, etc. So this is inner orbital complex. For this we have to make 2 d orbitals vacant available in 3D. Outer orbital D3. Then we have 4s, 4p and 4d. This is 3d, 4s, 4p, 4d. So already we have 2 d orbital left. So number of unpaired electron is 3. D4, because 3d orbital is not to be used. So number of unpaired electron is again 4. D5, we have 5 electrons. So number of unpaired electron is 5. So see the difference. In D3 we have same number of unpaired electrons. In D4 we have 2 inner orbital complex, but in case of outer orbital complex we have 4 unpaired electrons. D5 inner orbital 1 unpaired electron, outer orbital 5 unpaired electrons. D6, the 6 electrons will be pairing up here. So the number of unpaired electron is 4. D7, the 7th electron will undergo pairing. So number of unpaired electron is 3 here. D8, so D8, the number of unpaired electron is 2 here. So D8, that is, we have nickel plus 2. So nickel plus 2 having D8 configuration, even if in presence of strong field ligand, if electron is paired up here, then only one d orbital is available. But for this complex, 2 d orbital is required. So this nickel 2 plus, that is D8, always forms outer orbital complex. How you understand the point? So this is D8 configuration. We have 2 unpaired electrons in d orbital. If electron is forcefully paired up in presence of strong field ligand, then also only one d orbital will be available for hybridization. Octahedral complex requires 2 d orbitals to be vacant. So these nickel plus 2, whenever this nickel plus 2 forms complex, octahedral complex, it will always be outer orbital complex. So once we know this number of unpaired electrons and the electronic arrangement of this metal ion, we can easily calculate the spin only magnetic moment. So this is how inner orbital and outer orbital complex are formed in octahedral complex, and under what circumstance we form, that is depending on the nature of ligand. So this is octahedral. Now coming to tetrahedral and square planar complex. Then we come to square planar complex. Yeah, first we'll take a tetrahedral. Tetrahedral complex. Now in tetrahedral complex, the coordination number is 4. So if the coordination number is 4, the question may arise, okay, why not this be square planar? We'll take up later on. So we have this tetrahedral complex, coordination number 4. The number, since coordination number is 4, so number of hybrid orbitals should be 4. That means 4 vacant orbitals should be made available by the central atom. So the hybridization is sp3. So we have sp3. That means the central atom should make available 1 vacant s orbital and 3 vacant p orbital. So this we use s and p. Both these s and p orbital that is used, that must be from Valency cell. So the orbitals in the Valency cell, s and p orbitals in the Valency cell should be completely freed up by the central metal or the central metal ion, so that this gives you sp3 hybrid orbitals. 4 equivalent hybrid orbitals are formed. This can undergo sp3 hybridization to give this tetrahedral complex. Now take this example. Nickel tetracarbonyl. Carbon monoxide is a neutral ligand, so the oxidation state of nickel is 0. So nickel is in 0 oxidation state. So look at this, we have this nickel, atomic number 28, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s2. So this is the Valency cell. So we have 4p, 0, 4d, 0 unoccupied. Now look at this. This is the Valency cell. We say Valency cell s and p orbitals will be completely freed up. So under the influence of ligand in complex, this nickel under the influence of this cobalt forms this 3d10, 4s0, 4p0, 4d0. So this electron is forcefully transferred from 4s orbital to the 3d. By doing this, s and p orbitals in the Valency cell is completely freed up, which can be used for hybridization. So we have looked at this 3d10. Two, 4, 6, 8, 10. Then we have 4s. Then we have 4p. This is 4s. This is 3d. And this is 4p. Now this 1 4s orbital and 3 4p orbital undergoes intermixing to give you 4 equivalent sp3 hybrid orbitals. Now these sp3 hybrid orbitals forms bond with carbon monoxide. So we have carbon monoxide, and each carbon monoxide is transferring a pair of electrons to the vacant hybrid orbital. So if you look at this, under the influence of this carbon monoxide, to free up this 4s orbital, this electron is transferred from s orbital to the inertial d orbital. By doing this, electrons are completely paired up in 3d orbital. So since the electron is completely paired up 3d orbital, the number of unpaired electron is 0. So spin only magnetic moment is 0. So we have a low spin complex. In fact, this value is equals to the experimental value. So the theoretical value that we predict from this sp3 hybridization matches with the experimental value. Since the resultant spin only magnetic moment is 0, so this could be sp3 hybridization. If the spin only magnetic moment is some other values other than this 0, then that could not be sp3. There has to be some other configuration. So some other examples of tetrahedral complex is FeCl4, 4 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 2 MnCl4, etc. So this is how tetrahedral complex is formed in case of sp3 hybridization. Then we have square planar complex. Again, in the square planar complex, the coordination number is 4. So again, the problem will arise here. If the coordination number is 4, then this could be tetrahedral complex or this could be octahedral complex. Now we assume it is nickel tetracarbonyl is undergoing sp3 hybridization. By doing this, we calculate the number of unpaired electrons to be 0 and the theoretical value of spin only magnetic moment is 0, and this theoretical value of spin only magnetic moment matches with the experimental value. Now since from this experimental value we come to the conclusion that our prediction that this complex nickel tetracarbonyl being undergoing sp3 hybridization is correct. So that means this comes to the conclusion only from this experimental value of spin only magnetic moment. Now coming to this square planar complex having coordination number 4 undergoes dsp2 hybridization. Now this S and P, this is from the Valency shell, and this D, this is from n-1 D orbital. So again look at this. Since D is written first, that means this is inner shell orbital, and S and P, that is Valency shell. Now P has got 3 orbitals, X and Y. D has got 5 orbitals. That the question arises, or the problem or the difficulty arises, out of these 5 d orbitals, which d orbital should be selectively used, and out of these 3 p orbitals, which 2 p orbitals should be used for hybridization. Now the concept of hybridization says there should be maximum possible intermixing of hybrid orbitals. If the intermixing tendency is more, energy becomes less, bond forms will be stronger. If the intermixing tendency is less, then hybridization will be weak. So now to have this strong intermixing tendency or strong hybridization, these p orbital used in this hybrid orbitals will be px and py. If I use px and py, then this d orbital should be dx square y square. That means this dx square y square has its orientation along x axis and y axis. Those orbital having orientation along x can overlap with px. Those having orientation along y can have overlap with py. So this is the reason why we selectively use dx square y square and px and py, so that they have orientation along the same axis and they can undergo maximum overlap, resulting in the strong hybridization. So look at this. We'll take this by taking this example. Take this nickel tetracyanide. So we have this electronic configuration of nickel. So nickel in ground state, that is 3d8 4s2 4p0. Now this nickel is to be converted in nickel plus 2. So this being the outer shell, Valency shell, we have to remove electron from the Valency shell. So we left this 3d8 4s0 4p0. So we have this. This is 3d8. We have this 4s and we have this 4p. Now square planar complex says we have to feed up 1 n-1 d orbital, but if you look at this 3d8, we have no vacant d orbital in third shell. So under the influence of ligand, this nickel plus 2 in complex one of these d electron will be forcefully paired up, giving this structure. So we have one d orbital left. So look, so this is against the violation of Ohm's rule. So we have 3d 8 4s 4p. Now this n minus 1 d orbital is unoccupied, so this undergoes overlapping with 4s and 2 4p orbitals, giving you dsp2 hybridization. Now we have 4 vacant hybrid orbitals. These combines with cyanide ion Cn minus, Cn minus, Cn minus and Cn minus, and each ligand is transferring a pair of electrons to the vacant d orbital, and this gives you the complex. So this is the formation of complex in nickel under this square planar. Now look at this. When we consider this square planar complex, the number of unpaired electrons, is 0. Since the number of unpaired electrons is 0, spin only magnetic moment is again 0. Now this spin only magnetic moment, that is the theoretical value. This is equals to the experimental value. Now if we consider this complex to be tetrahedral, if we compare this to be tetrahedral, then there should be 2 unpaired electrons. Due to the presence of these 2 unpaired electrons, there should have been some spin only magnetic moment. But the experimental value of the spin only magnetic moment says this complex NiCN4 2 minus, the spin only magnetic moment is 0, and the theoretically predicted by certain, assuming this to be square planar complex having dsp2 again comes out to be 0. Now since the experimental value matches with the theoretical value, so we can certainly say this complex NiCN4 2 minus, this is square planar complex having this hybridization. So this is how square planar complex, tetrahedral complex and the octahedral inner orbital and outer orbital complex are formed in coordination compounds. So this is what we call as the valency bond theory. So valency bond theory mainly depends on the hybridization stage. So before this hybridization, the central metal makes freed up some unoccupied vacant orbitals, and that orbital has to undergo intermixing, and after this intermixing that will form hybrid orbitals, and these hybrid orbitals are oriented in space in such a way that distance between the orbital is maximum. If the distance is maximum, energy is minimum. If the energy is minimum, that particular state will be the most stable form. So that gives rise to the structure, shape or the geometry of the complex. Now having learned this, we'll see what are the main demerits, because already we have discussed the hybridization, and based on this hybridization we say we can predict the shape or geometry, we can predict the hybridization state, we can predict the electronic arrangement of the central metal ion in the complex. Based on this electronic arrangement, we can predict the magnetic behavior. If the complex contains unpaired electrons, then that shows magnetic behavior, that is paramagnetic, or if there is no unpaired electrons, then we say this is diamagnetic. But apart from this, there are some disadvantages or demerits. Disadvantage or demerits of this valency bond theory, VBT. First, let's see one by one. Valency bond theory or the VBT does not say anything about the color of this complex, because most of the complex species are colored. And why complex species or transition elements and their compounds are color. So this says nothing about the spectra. Says nothing about the spectra or the complex of color of the complex. Second, it says nothing about coordination number 4. If the coordination number is 4, suppose okay, we just discussed, if the coordination number is 4, then this can be square planar or this can be tetrahedral. So these valence bond theory cannot differentiate between these two. Valence bond theory cannot differentiate between square planar and tetrahedral complex. That is, if the coordination number of the central metal is 4. That is, we just assume that one has to undergo tetrahedral and one has to undergo square planar. Then we find the spin or the magnetic moment. Then we compare with that experimental value. Only after this experimental value we can say whether this is tetrahedral or this is square planar. But just by looking at the complex, we cannot differentiate whether this is square planar or tetrahedral. Then again, look at this. In octahedral complex, we have two types of complex: inner orbital complex and outer orbital complex. So again, look at this. Why some octahedral complex is inner orbital? Why some of the tetrahedral coordination number 6 octahedral complex is outer orbital? So these use of inner orbital or the concept of outer orbital cannot be differentiated by use of this valence bond theory. So coordination number 6. So we have outer orbital, we have inner orbital, sp3, d2, d2, sp3. So again, cannot differentiate. So means why some complex uses n-1d orbital, why some complex use n-d orbital. That is basically depending on the nature of ligand. So for this, and valence bond theory doesn't say anything about the nature of ligand. Says nothing about the nature of ligand, whether this ligand is strong field ligand or weak field ligand. It says nothing about the nature of ligand. Number 5. Now look at this. This valence bond theory focus mainly on the central atom without any consideration of the ligand's atoms. Mainly focus on the central metal. Focus mainly on central metal orbitals without any consideration of the orbitals of the ligand. So these are some of the disadvantages of this valency bond. Means main focus is on the central metal, and they do only the valence shell orbitals, and with regard to the other orbitals and the orbitals of ligand, it has nothing to do with. So these are some disadvantages. Apart from this disadvantage, I told you there are some advantages, like we can predict the shape, we can predict the geometry, we can calculate the electronic structure. Based on this electronic structure, we can predict whether the complex will be paramagnetic or whether the complex will be diamagnetic. So for this, apart from this, we have these types of disadvantages. So this is a brief idea about the valency bond theory. What is valency bond theory? What are the postulates of valency bond theory? What are different types of complex that is formed, and how the hybridization occurs, and after formation of hybridization, how this interacts with the ligand orbitals to form the sigma bond. Then we can predict the geometry or the shape based on the arrangement of these hybrid orbitals in space. Then from this electronic configuration, how we define the magnetic behavior of the complex, then under certain conditions how this forcefully pairing of electrons occurs, that is the violation of Hund's rule. So this is something about the valency bond theory. Hope you will enjoy it. Let's take up the other theory in the next class. Thank you.